Technology, Missouri University Science and Technology.
You must say that.
I know. I was hoping not to say must because I know you guys don't like the must.
Yeah.
So, but Jonathan, I mean, he got his PhD here. At the same time, he was working in the lab. So he knows Illinois very well, and we're very happy he's here. I'm going to ask this out of respect. Just please put your cell phones and tablets and all that crap away and pay attention to the presentation. Okay?
Because of the exam at the end.
Precisely.
Short quiz.
Okay?
Short quiz, yeah.
I'm going to start actually making that announcement. Let me actually put it here, so because there'll be people that will come late. So, no electronic devices, idiot.
So, well, and thanks for having me. As you said, I was, so first I got my master's here back in the 90s, went and worked in industry, came back, was a research engineer, and got my PhD, and I've been at Missouri S&T ever since, so about 11 years now, coming up on. And so I thought what I'd do today is kind of give an overview of what my research program is like now. Some of the topics I've been working on, that sort of thing. There we go. So I'll do a little brief talk about multiple reference frames and some control algorithms and modeling, and then I'll get into a couple of applications I've been working on. This is, I'm sure, familiar to most of the people in this room. We have the Clark transformation that takes the ABC into an alpha, beta, gamma, and there's either the power conserving or non-power conserving variation. And then we have the alpha beta part where we discard the zero sequence, the gamma. And in that case, we no longer have an inverse, but we do have a pseudo inverse. That's what the plus stands for, is a pseudo inverse. And one weird thing about pseudo inverses is there can be left and right pseudo inverses. So in this case, if you multiply by it on the right, you get the identity matrix. On the left, you get this other matrix.
What do you know about Edith Clark? What do you know about Edith Clark?
Was she at RCA or GE? I think she was at GE.
She was in Texas in the latter part of her life.
That may be. I managed to dig up the original paper that she published in 35, yeah, something like that. Because I wanted to go back to the basics. The reason I'm putting this up here is a few years ago, I started working with these, and there's a lot of inconsistency in the literature. And I was trying to get my head around, okay, where does this all come from? And so I went back to the source. All right. So this was Edith Clark's work. I believe that she used the non-power invariant, and then somebody figured out that if we use the power invariant, it becomes a unitary transformation where the inverse is the transpose.
I don't think she ever wrote anything with a matrix notation.
I believe you're right. Yeah. Okay. The Park transformation is where things kind of go off the rails in the literature, because there's the DQ and there's the QD, and then do you have the Q aligned with the real axis or the imaginary axis and everything. So I wanted to kind of put a stake in the ground that if we see that all it is a rotation matrix that you learn about in trigonometry, right? And if you see it that way, then it naturally aligns the D axis with the real axis and the Q axis at plus J, as opposed to the QD0 that has D at negative J, which never makes sense to me. Okay. Why I wanted to to do all this was to introduce this X as an arbitrary harmonic. And where I'm going is multiple reference frames that we talked about earlier with Dr. Banerjee, that typically X is going to be an integer. Typically, omega is constant in some applications, a PLL in some applications, or just a free variable in a motor or generator kind of application. In which case, you have to use the integral form here.
Omega, I thought, was fixed.
It depends. It depends on what your system is. So one application that I'll talk about later on is where it's kind of like a UPS where you're producing a fixed frequency output. And in that case, omega is fixed. In the case of the grid, it's not really fixed. It's close, but it's not really. Now, some people say, how can you talk about the frequency of something that's not periodic? But it just doesn't change very much. And so we use this integral form. All right, for the rest of what I'm going to talk about, I'm going to throw away the zero sequence or the gamma component. Okay. So here's the multiple reference frame theory, and this goes back to Pat Chapman's work with Sudoff. Pat was a professor here when I was getting my PhD, and this came up in the context of machine control, motor control, and that is we can represent an unbalanced and/or distorted three-phase set as a harmonic sequence. Okay, so what we have here is DQ components of a harmonic series. Okay, and this would be the typical harmonic series if you have a balanced three-phase set, where it's 2n plus 1, right? So you have the -5 and the +7 go together and so forth. And then your total ABC is you take that harmonic series, rotate it back to the stationary frame, sum it up, and now we have an alpha beta total. Do the inverse Clark, add back your zero sequence, and you have your ABC. All right. So the problem is, Pete, just in time to hear about reference frames. All right. So the problem is that there's no mathematical transformation you can do to go from the ABC to this harmonic sequence of DQ. So what do you do? And that's where this estimator comes in. What you do is you estimate each component, add it up, and feed it back as your total, and like this. So this is for each rotating frame. You have one of these estimators. You take your total alpha beta of your estimate and of your actual, compare them, rotate them into your relevant reference frame, apply a PI, so they should be constant. So that error in that harmonic should be 0 if you have properly estimated the constant component. All right, and then now you have this DQ. You can rotate it back. Now you have the xth harmonic in the alpha beta, and you sum those up to get the total. All right. There's a causality problem. If you just implemented it like that, you would end up with an algebraic loop. Okay. And so to break that algebraic loop, we put a unit delay in it, and to account for the unit delay, we'll have this delta. We'll talk about that in a second. All right. So these are just some variable definitions. There's our total error, and then we rotate the error into the X harmonic frame. After we integrate that error, we end up with the X alpha beta component from the X DQ, and then we have the error in the DQ and our total alpha beta estimate. Okay. Yeah.
One quick question. Yeah. Is it similar to a three-phase PLL but locked at multiple frequencies? Like if I can drive
Similar.
to 0,
Similar.
lock it for 3 different frequencies.
Yeah. Yeah. No, it's not quite, but it's similar. Let me see how to explain the difference. So in the three-phase PLL, what you're varying is the frequency, right? And here what you're varying is the harmonic component, but the end result is the same, is that your error should go to 0 if you are locked correctly.
Right, so if I put that theta as 3 theta, 5 theta, I should get all those harmonics.
Right. Yeah, and so that's what this is you have capital N different harmonics that you're adding up to estimate the total. So you're splitting your arbitrary waveform into its components. Okay. So the question is, does it work? And I borrowed from Pat's approach to analyzing it. Basically, if you sum up the error dynamics in each reference frame, you will get this same equation, and then you add all n of those together, and you'll get an equation that has this characteristic polynomial. And so as long as the root of this gives you a pole inside the unit circle, or a pair of poles inside the unit circle, we have a stable estimator. Not only that, we can use this to build a model that it's not real accurate, but it's good enough to do some design work with, to get you close to a total system transfer function.
Does this equation always have real solutions?
No. Right, because it depends on your relative proportional integral gains. And in actuality, I included proportional gain here, but don't usually use it. Usually you set it to 0, in which case you'll have see a pole at the origin and then another pole. Okay, so I mentioned that delta. So the problem with this is the delay. Now, when Pat was doing this back in the 90s, he was only concerned with maybe out to the 7th harmonic of a 60 hertz waveform, and switching at like 10 kilohertz or something. And so he didn't have to deal with this issue. But if we look at the 19th harmonic of 60 hertz, if we only have 5 kilohertz switching, 1 unit delay is 164 degrees. This second line, this is what drove me down this road. Doing a 400 hertz inverter with 12 kilohertz switching, if you care about the 13th harmonic, which is pretty substantial in a lot of applications, that's almost a full rotation, right? So we have some Nyquist things going on that I need to deal with, but setting that aside, we can partially compensate for this delay effect by just advancing our estimates by some angle delta using the rotation matrix. Okay, and what that does is helps recover some of the phase margin that you would otherwise lose in your control loop. So I kept finding that I couldn't stabilize my control loop until I added in this phase advance, and that recovered enough phase that I could make a stable controller. So this is just an example. So what I did, this is just an estimator without a controller that goes with it. But so I created an arbitrary waveform, and the dashes indicate the components of that arbitrary waveform. And when you start the estimator at 0.25 seconds. You see it has a classic second order type response with some other interesting stuff. And so that characteristic equation captures most of that second order response, but it doesn't capture all of the interactions among the harmonics, because they can oscillate against each other in the estimation process. Okay, that was a pretty quick tour through this multiple reference frame stuff. And the reason I wanted to do that was just to establish a baseline of, we're going to be looking at applications where there's imbalance, where there are harmonics, and we need some tool to enable us to get our hands on those harmonics. And this multiple reference frame synchronous estimator is a good tool to grab onto that information. And then you can kind of partition your system into this harmonic sequence, control each harmonic, sum it all together, and move on. Does that make sense? See a few nodding heads. All right. So let me move on from there to some control algorithms that we've been working on lately. And I'll first say that there's plenty of methods in the literature for controlling a grid-tied inverter. But there's a couple I've been looking at that fit in this real well, and I've been able to implement using the multiple reference frame. And we can use either an inductor to connect to the grid or an LCL filter for a grid tie. That should be a dot. That should be a dot product. Okay, so the first one I want to talk about is parameter estimation. So basically, we can compute these quantities M and N from measurements of the voltage at the inverter end of the inductor and the current going into the grid. We can also compute those same quantities from some known inductance and resistance. Okay, but we don't know the inductance and resistance. And so hey, come on in. We met this morning out at the Ameren Tax and told them about this. So at any rate, we don't actually know the inductance and resistance, but we can use that knowledge that we have from the two different perspectives on it to compute our estimated resistance and inductance. That's important because when we're doing all of our control in this harmonic series, as we get to higher order harmonics, the inductance especially matters a lot, and so we need to have accurate examples or accurate estimates of it. So here's just a preliminary result. This one is we had some resistance and we switched the resistance, and we see that we can estimate the change in resistance. Still working on getting results on changing the reactance. And then here is, okay, so we use one of these methods that kind of feeds forward the parameter values. And if we just use like nameplate, inductance, and resistance, a feed forward method really doesn't work. It gets close, but it doesn't work. But then once you enable the estimation, we get good convergence. Okay. And then this is a method that I see a lot of connections to some work I'm doing at the system level using energy methods. So this is a Lyapunov function. Well, at least we want it to be a Lyapunov function. The way we make it a Lyapunov function is by adding some resistance here. Okay, these resistances, once you compute the derivative of this function, if you include these resistances, the derivative becomes negative definite. Okay. One challenge we have here is this VS star is the feed forward voltage we would want to apply. Okay, so that's if we knew what the inductor and capacitor values were and everything, that would be exactly right. Okay, but we don't know those values, so of course we need some way to compensate for it. Well, but if we could get better estimates of L2, RL2, CF, L1, RL1, if we could get better estimates of those, then we could more accurately control this out at higher frequencies. Okay. And here again are some preliminary results. So here is a case with distorted voltage, where we just control the fundamental current. And then here's a case where we have basically clean voltage, and we apply a step command to the grid current. Okay. So some things I'm looking at in the near term. So we have this parameter estimation that only works for a system that has just an inductor between the inverter and the grid. Okay. Well, that's not very practical. Typically, you'll have an LCL filter to get a cleaner grid side current. So we need to expand our parameter estimation to deal with this LCL filter. We've developed a couple of different methods for estimating the grid voltage, which, okay, yeah, we want to sense the grid voltage. That's an important thing in a grid tied inverter. But where do you sense that voltage? Well, typically you'll sense it right at the terminals, but then there's some impedance between there and any hypothetical distant voltage source. And so we can incorporate the Thevenin equivalent impedance of the system if we're estimating that grid voltage further away. And then the last thing is the delay, like I mentioned. So in principle, if you do the Lyapunov analysis, as long as RC and RD are positive, everything works great. But in practice, if they're too large, it becomes unstable, and the reason is because of the delay that's inherent to the discrete time implementation, even with the compensation for that one step ahead. So we need to work on that aspect of it. Okay, so again, my goal here is to kind of give you a flavor of what my research program is. So I kind of work on grid-tied systems starting from the power converter. And that's what I've talked about here, is we have some power converter, and the grid-tied inverter might be connected to a PV or wind turbine. It may be connected to a battery bank or something of that nature. Okay, but then connects to the grid. Well, what kind of grid does it connect to? Let's look at a microgrid that might have many of these devices on it. Okay, so expand the scope of our work a little bit. So instead of just looking at one device, let's look at multiple devices. And we have two scenarios when we have multiple devices. One is that the devices are all communicating with each other and acting in some coordinated fashion. And so how do we make sure that they coordinate appropriately? The other is that they're not communicating with each other, and so we have to use some sort of stochastic analysis of them. So let me start with the coordinated case. So this is this is more general than just the microgrid or grid connected inverter case. But if we have a switch system with multiple operating points. How do we speak about its stability? Well, most switch system literature assumes that you have a system whose dynamics change, but you're always concerned about the same steady state operating point, the same stable origin, right? The origin doesn't change when you switch. Well, the switch system we're going to come up with here is we take a nonlinear model of a microgrid or other power conversion system, and we linearize it around multiple operating points. Okay. Well, so each of those linearizations is locally stable around a particular origin, but those origins are all different. And so when you switch the system, not only do you switch the dynamics, but you also switch where the origin is. And that switching could cause instability.
So you need to also, on top of the switch model, I mean the standard model, you need some reset maps for the states?
Right, which I think is in the next slide. It's in here somewhere. At any rate, so the way I've dealt with the reset map is that it resets the reset map is only for basically the index, the I index. The states, the small signal states change, but the large signal states do not. Does that make sense?
Yes, because of the point around which you are linearizing.
Right.
But where are the reset maps encoded here?
They're not. They're not on. They didn't make it on this slide.
So it would be on the small xi tildes, right?
Right.
Yeah.
Right. So basically, your small signal state, there's an impulse or a reset map. It's the difference between capital X of the previous mode and the next mode. Yeah. Yeah. Yeah.
But if you move from one point in the state space to another point which is far away, and you are linearizing, how good is that model of linearization? If you are too far from these two switch states, xi1 and xi2, you can be really non-linear in that region.
That is true. I'll talk about that in just a minute. Yeah. Okay. So, but here's our switch linearized model. So we start with some nonlinear model, and then our ith mode is defined by some constant input capital U. And for that constant input capital U, we have some steady state operating point capital X, and then some incremental small signal portion. And that small signal portion is governed by linear dynamics. For linear dynamics, we can find a Lyapunov function of this form, as long as P satisfies this relationship. If P is a positive definite symmetric matrix and Q is a positive definite symmetric matrix, and that satisfies, and they satisfy this relationship, then here's our derivative of V.
That's for each of the modes.
Right.
But globally, what can you say? Because I mean, the standard approach is to find the common Lyapunov function, but that's not what you're doing here.
That's correct.
Okay. So what about when you have multiple Lyapunov functions like this?
Right. So that's what this is. All right. So let's imagine for a moment. Let's just talk about one mode for now. So here is our capital X, our steady state operating point. Okay. And then we have those look. Yeah. Okay. These two are circles. Okay. Do they look like circles to you? All right. They're skewed from here. At any rate, so the level set of one of these quadratic functions is an ellipsoid. And so we define two ellipsoids, a small one and a big one. Okay. and we'll use lowercase letters anytime I'm talking about the smaller one, and uppercase whenever I'm talking about the larger ones. Okay, so given a particular choice of this smaller level set and this larger level set, we can find the time it takes to go from the outer level set to the inner level set. It's a loose bound, but at least it's a bound. Okay.
What are those level sets for exactly? I mean, what do you mean by small h and large h?
Okay, so this will probably make more sense here. Yeah, let me do this and then come back to that one. All right. Here's our objective. We want to know if we switch from state one, from mode 1 to mode 2, how long will it take for that transition, for the continuous states to get close to the new operating point? Okay, and what do we mean by close? Okay, so here it is. Here's one steady state operating point, a small ball and a big ball. And these balls are chosen so that if you're inside the small ball of one mode, you're guaranteed to be inside the large ball of the other mode, right? So you notice that this mode, you have to be inside this smaller ball in order to get inside this big ball around this mode. Okay, so that's
using mode in the eigenvalue, eigenvector sense?
no, using mode as the discrete state of a hybrid system. Okay, so now we're looking at just one of those modes, right? So here's that small ball and big ball of the other slide. The smaller ball is circumscribed around this level set. The larger ball is inscribed in this level set. Okay, so we know that if we're inside this ball, we must be inside this level set. Okay, and then given this exponential bound on the decay of the Lyapunov function, we know that if we wait long enough, we'll be inside this smaller level set. And we know that if we're inside this smaller level set, we must be inside this ball. Does that make sense?
I understand your inequality there at the top.
Oh, this here?
Yeah. Both Pn and Qn are positive definite.
Yes.
So that lambda n has to be a positive number.
Right.
And then you get there that it's going to tend to something which is bounded by a negative number.
This is a derivative.
That's just the rate of decay.
This is decay rate.
Yeah. That's pretty standard result. The lambda max over P and lambda min, that's pretty standard.
Yeah. Okay. All right. So again, our objective here is to analyze a system that can switch among these different operating modes. Okay, and for each set of inputs, we have some different stable operating point. And so we need to make sure that we wait long enough that we're close enough to that new operating point that we can switch safely. All right. So there's some challenges here. One is that exponential bound that I had, which is, I mean, it's pretty standard, but it's also pretty poor. Okay, and it depends on the conditioning of the system. So those ellipsoids I drew were pretty round, really. Sometimes the ellipsoids end up looking like a line because they're so long and skinny. And that causes a real problem. That makes the exponential bound extremely loose. In which case, we're doing some other things with approximate decay rates and things like that. If we have a system that has many possible operating modes, we get this explosion in discrete states that becomes just unmanageable. So what we're looking at there is, instead of a point, looking at a compact set of possible points. And then the last thing is the optimal ball selection. So it's a constrained multi-objective optimization. Is you need to pick both the small balls and the big balls, and you want to make sure that all the small balls are inside all the big balls. Okay, but how big and how small, right? And the how big comes back to your question about what happens if you switch and you're very far from your stable operating point. Your linearization may not be very good. Okay, so that's pushing you to make all of your big balls as small as possible. But the time that you have to wait depends on the ratio of the sizes. And so if your small balls get too small, then your dwell time gets too large. And so it's like I said, a constrained multi-objective optimization. Did I answer your question? You were asking stuff, yeah. Yeah, good. All right. Okay.
Basically, what you're doing, if I understand this correctly, is that you if you wait long enough, you go inside these balls that once you do the switching will allow you to converge asymptotically to the equilibrium point of the new configuration.
Right.
How long you wait? Well, this is given by that Lyapunov, the
decay rate.
on
Yeah.
the Lyapunov function.
That's right. That's right. Where I started down this road is I've been working for almost as long as I've been at S&T with a guy in computer science on cyber-physical systems. Okay. Our idea is that we can use this this analysis and this dwell time as a constraint on the cyber system. So the assumption is that there's some communication among all the devices coordinating the next switching event, that dispatching the PV or the battery or the whatever, and we can guard and not allow a cyber action until a sufficient time has elapsed in order to guarantee stability. Okay. This I'm going to go through quickly, but I will note we have this reset map. I'm sure you've seen this because this comes out of your paper, I think. So I was presenting work similar to the previous work at ACC several years ago, and Sairaj Dopli came up to me afterwards and said, well, there's this other way. So I've been working on these stochastic hybrid systems since then, and that is where you have a stochastic, a Markov process that determines this switching rather than a cyber process that's coordinated in some way. So it's just totally random. And we look at the dynamics of the moments of the states. And I guess the main contribution we've made is getting everything nice and matrified. So if we limit ourselves to talking about these switched linear systems, we can algorithmically, put things into matrix form. The main challenge we run into is just the size of the matrices, right? If you have 5 continuous states and 2 modes, you only have 10 first moments to worry about, but you have I don't know, 20 or so, or no. I think you have like 50 second order moments, and then third order moments is just becomes unreasonable.
Yeah, but the assumption is you're assuming linear system, the A and B are constant, right? They are not time varying, and
Right.
the transition rates are constant, makes it the Markov-Champaign process. But what about the reset maps? Do you have reset maps here?
And
So it's
just
just
that.
they are not there.
Right. And the reset map that we would have needed in the other is lumped into this C matrix. So again, we keep X, our continuous states are smooth, and then we change this C to deal with that. And so, like I said, we can construct these matrices. What gets wacky is dealing with redundant second moments. So we have moments of this form equal moments of this form, and so we have to remove those redundancies. And then, like I said, we can do the same thing in the for third order and nth order moments, but the matrices get large. All right. I think so I want to talk about a couple of applications, because all of these things come out of other projects I've been doing. It's like, okay, I need a tool to analyze this thing, so let me go find a tool. So here are a couple of the problems that I'm working on. This first one is ground support equipment for aircraft. So aircraft power systems are 400 hertz, three-phase. Okay, and where that comes from when they're in the air is a generator that's on the turbine shaft, or maybe they have a separate engine that just runs the generator. Well, they can't do that when they're on the ground. They can't run their engines on the ground. So, like at an airport, they have a big cable that they plug in that provides that power. Well, so here are the specifications on that: 400 hertz, 200 volt three-phase, 90 kVA, up to 400% overload with tight control of harmonics and unbalance. So this tight control of harmonics and unbalance is what pushed me down the road of the multiple reference frame stuff. And the 400 hertz at this voltage means that I'm using IGBTs that aren't that fast in the whole scheme of things. So we have this. Yeah.
Before you go,
yeah.
Here, is there a specification on the timing, like 400% overload? Is this for a specific time?
Yeah, the 400% is for like 1 second, I think. Okay, but that's still a long time from power electronics standpoint, and it's like 300% for 10 seconds, which,
so there is an envelope.
Yeah, there's an envelope, yeah. So, it's not unreasonable to have 19th harmonic content in a nonlinear load, like a 6-pulse rectifier. So that's 7,600 hertz. So we're pushing our bandwidth here. And silicon carbide we looked at, but they're too expensive right now for this application. So IGBTs are maybe switching at 12 kilohertz. You can't possibly even sense the 19th harmonic then. So what do we do? So what I've come up with is we have a 3-level H bridge. So that ends up being a 5-level waveform that goes out. The 5-level waveform itself gives you reduced harmonics. And then I have 4 switching edges per period. So even though we're switching at 12 kilohertz, we can update at 24 kilohertz and get reasonable control. So again, the relevance, the multiple reference frames to control all the harmonic content. The active front end uses that Lyapunov-based control that I mentioned earlier, but the output side is just a conventional PI in that harmonic sequence. Okay, and this is the new and exciting thing that I'm getting started on: extreme fast charging of electric vehicles. What does that mean? 350 kilowatts so we can recharge an electric vehicle in about 10 minutes, which would be like filling up a car with gas, right? You pull into the charging station, plug in, go in, get a drink, use the restroom, stretch your legs, then your thing's done, and you get back on the road. Okay, so there's a lot of challenges there, but let's start with it's 1,000 volt, 350 amps on the output side there. The reason is if you use like 600 volts, the current would push you to a cable that's so big that you can't handle it. You know, imagine a little old lady with a cable this big around trying to plug it in, right? So to try to keep the cable size manageable, we push the voltage up. The other thing is that, you know, you wouldn't have just one of these chargers. Dr. Gross was saying that Meyer has 8 Tesla supercharger stations. Well, we're just looking at 3, but 3 times 350 kilowatts is over a megawatt. Okay, and you can't just plop down a megawatt load wherever you want on the grid, right? Yeah.
One more question. So 1 kV, isn't there a safety concern here? Like, will I be able
Yeah, I'm a little worried about that. So my brother-in-law is a lineman, and he said, "Man, I'm going to need my gloves and sleeves just to fill up my car." But I expect that in the short run, these would be manned charging stations, not unmanned. That you would have somebody come out and plug you in. But yeah, that whole aspect of it we need to think about. But first we need to get to the point where this is even possible, and then we can come up with safety protocols. But yeah, the 1,000 volt battery pack is a little bit terrifying. Yeah. So here's just a conceptual picture. So what we'll do is we'll come straight in off the distribution feeder into our converter here. We'll have a stationary battery that softens those edges. So when you plug in, you have a 350 kilowatt step, and all of a sudden the distribution grid just goes crazy. Well, we have a stationary battery to smooth off those edges. Have, you know, these 3 stations that you plug in your car, and not shown as the convenience store where you get whatever. Okay, so we have our direct connection to a 15 kV class distribution. We're going to do the full-scale demonstration at the Ameren TAC, where they have, it's 12.47, right? And so does, we're working with Bitrode, which is in St. Louis, and they're also on a 12.47 feeder. We'll have a cascaded H bridge on the input and a many-phase dual active bridge with the outputs paralleled to give us a 1250 volt DC bus. And then from that 1250 volts, we'll regulate down to the 1,000 volts. There'll be 3 vehicle ports and 1 connected to this energy buffering port. Okay, so our challenges and our team. So the batteries, can the batteries take it? I don't have a good answer for that question. Nobody has a good answer for that question. This is like 6 times the 1 hour charging rate, right? Because charging in 10 minutes, can the batteries handle that? I don't know. That's why we're working with LG Chem, which is a major manufacturer of batteries. They made the stationary battery that's at the Ameren TAC, actually. And then Robert Landers and Jong-Hyun Park are mechanical engineering professors that study battery degradation. On the power conversion side, we're working with Bitrode. Bitrode makes mostly lab grade and end-of-line production type battery charging devices. This would be their first foray into consumer type battery charging. And then Mehdi Firdousi and Poria Shamsi are faculty at S&T that do power electronics. And then we need to do something on that grid side, and that's why we're working with Ameren. And Ray Bowe is a relatively new faculty member, used to work at MISO. It's good at analyzing the grid requirements. So again, the relevance, the AFE will use something similar to that Lyapunov control with some centralist voltage estimation to account for the grid impedance, the switch system model to evaluate the grid stability. So just to kind of summarize, so there's lots of applications that all have similar approaches, but with unique challenges. The multiple reference frames give us enable us to analyze the harmonics and on balance. We have bandwidth issues, and we have to deal with this medium voltage as well. And then if we step above the individual device, we have the switched and stochastic system type of modeling. I want to acknowledge my students. Vikram is a current PhD student. Jake he graduated in May, and he's a postdoc at Sandia National Lab in support of NSF and Department of Energy. Thanks. Pete.
We've got a guy here, his name is Paul Braun.
Okay.
He works in material science.
Uh-huh.
He's the Mr. Battery charging wizard. You could go down there and see him and ask him that question. I'm sure he'll give you an answer on the spot. But he's doing research in super fast charging, whether it's lithium ion or I'm not sure what it is. But Paul Braun is his name.
Braun, B-R-A-U-N?
Yeah, yeah.
Okay.
And I'm sure he'd love to see you,
Okay.
especially with your connections to the TAC.
Yeah.
So he's my neighbor, so if you want to come home with me, you'll be able to.
And he has a startup company, so if you're really interested in that.
Oh, okay.
All right, we need to get out of here because of the class that comes up.